Yeah. Hi everyone. Good evening. Welcome back to our weekly series where we talk about the various projects. And now, in front of you, today we have one project, pallet detection and counting. So first, let me introduce myself. Myself, Kunal Gokul Borse, and I'm working as a trainer at 360DigiTMG and also junior data scientist at AiSPRY. So So in this slide, let's talk about the one scenario. So here we have two people who are competing for the job, Mr. A and we have Mr. 360. So the Mr. A who trained at XYZ Institute, who worked on the dummy project from the Kaggle, GitHub, etc. And on the other side, we have Mr. 360, who trained at 360 DigiTMG, who worked on a real-time projects, attended daily stand-up calls, created end-to-end data pipeline, deployment on premises and on cloud, attended daily client meetings, research paper published in international journals. So here you can see the clear difference between these two. And you can take a guess for yourself as who will get shortlisted for the job and whose resume will get shortlisted. Okay. So, without any delay, let's move further with our project. So, the project name is Pallet Detection and Counting. So, our client is one of the leading pallet manufacturers. So, the business problem we have here is so there is a company who makes pallets, especially a wooden pallets. So, these pallets used to carry some stuff like boxes and goods. You can see in this image, this is a pallet. This is a single pallet. Okay. So now they are having a big issue. So they store these pallets in their warehouses by stacking them on top of each other. So the problem is they don't have a good way to keep track of how many pallets they have in their warehouses. Right now, workers are either counting them manually or using some old tools, and those methods are not giving the accurate count. Because of this, they often don't know the exact number of pallets in their stock. So that leads to the mistake like delaying shipping, sending the wrong number of pallets, or even paying extra money because of some stock error. To make things worse, the machines they use, they can't really see how many pallets are stacked on top of each other. So they need some AI solution on this business problem. So and for this, we have some business objectives where we have to minimize the latency of count and maximize PCS accuracy. The constraints to minimize the processing time. And we have some success criteria like a business success criteria, machine learning success criteria, economic success criteria. So the business success criteria is to achieve the 25% reduction in overall warehouse operational cost, including labor and counting inefficiency. The machine learning success criteria is to achieve at least a 90% of model accuracy with an inference time of less than or equal to 1 second per frame. And the economic success criteria is to achieve at least 30% reduction in operational cost, including labor and inventory loss. Okay. So next, so for that, we have implemented high level solution. So implemented an AI powered vision system using a deep learning and computer vision to accurately count the stack pallets in the real time, which improving the inventory management and operational efficiency. So next, we have the high level design. Okay, or we can say that the high level architecture diagram. So this is the high level architecture diagram that provides a pictorial representation of our project flow following the CRISP MLQ methodology. It begins with the business and data understanding and followed by the data collection and store in the S3 bucket. So next, we perform the data pre-processing, including the annotation and augmentation using the RoboFlow tool. Okay. So then we proceed to the model building and we build some models using the Ultralytics YOLO model. Okay. And then evaluated the best performing model and deployed it using the Streamlit framework. Okay. And finally, we included the monitoring and maintenance and handed over the complete solution to the client. Okay. So this is the stack palette data we have collected. And next, just let's understand about the data set we were using. Okay. So we have collected over 250 high resolution images, 250 plus high resolution images of the palettes, which increases to 3,741 images after annotation and augmentation. The data is unstructured, mainly consisting of front view images of the stack palette. So these images were gathered from the online websites. Okay. And the key variables, which includes the palette count, stacking patterns, and changes in lighting and camera angles. Okay. So during initial analysis, we observed that although palettes have consistent structure, they differ in alignment and stacking position. So additionally, shadows and block views made detection more challenging, which required a strong and careful model building. Okay. So the next part is data annotation. Okay. So after collecting the data, we have pushed data into the RoboFlow for the annotation and augmentation. So we perform annotation using the RoboFlow, as I already mentioned. And for annotation, we choose the polygon tool over bounding boxes because palettes have some irregular edges and varying orientations. Okay. So bounding boxes would have included unnecessary background elements, reducing model accuracy. The polygon tool allows the precise segmentation and improving the detection performance. And we have only one class, which is nothing but the palette. Okay. So after annotation, we move towards the augmentation to increase our data set. Okay. So in the augmentation, first we applied some default pre-processing steps, such as auto orientation the images and resizing them to 640 by 640 pixel to ensure the consistency and improve the model performance. To enhance the model's ability to generalize the performance, perform in the real world scenario. So we created 4 versions of augmented data: version 1, version 2, version 3, version 4. Okay. Each version included the different transformations like changes in brightness, rotation, blur, saturation, grayscale conversion, and horizontal flip like that. So these augmentation helped to create a different lighting angles, noise, and color effect in the image, making the model more robust and accurate in detecting the palettes. Okay, and then later we split the data into 3 phases. Okay, so we divided the data into training, testing, and validation to ensure the data to ensure a balanced and effective process. Okay, so in the training we have 2,993 images, and testing and validation we have 374 images each. Okay, and these are nothing but the augmentation techniques we use: blur, noise, saturation, exposure, flip. Okay, blur, noise, grayscale, shear. These are nothing but the augmentation process, augmentation techniques. Okay, so later we move to the model building phase. Okay, so we trained a following YOLO model for the detection, which is supported by the ultralytics. So we trained YOLO V8 large, YOLO V8 medium, YOLO V8 nano, YOLO V8 YOLO V9 compact, YOLO 11 medium, with each model with the 50 epochs, and we get the accuracy as like shown in this table. So for the accuracy matrix, we use the some following evaluation metrics like mean average precision 50, mean average precision 50 to 95, precision, recall, and the confusion metrics we use. Okay, so based on the accuracy, we have chosen YOLO V8 large model with the 50 epochs as the base model for the pilot detection and counting. Okay, so which gets MAP 50 up to 99.4%, MAP 50 to 95 up to 83%. Precision is up to 98%, and recall is 98%. Okay, and then we perform the hyperparameter tuning on this selected model, which is YOLO V8 large model. Okay, so we experimented with the key hyperparameters like initial learning rate, uh, final learning rate, seed, warm-up epochs, okay, etc. was added and further trained with the 50 more epochs by taking the base.pt, which is the outcome of the of previous YOLO V8. Okay. So we took a GPT, which is outcome of previous YOLO V8 large model, which we have trained already by adding or by enabling the pre-train equal to true with batch size of 60. Okay. And we get some results after hyperparameter tuning. Here you can see MVP 50 is 99.6% now, and MVP 50 to 95 is 85%. Precision is 99%, and recall is 98.9%. So we have increased the accuracy by 1 or 2%. 1 to 2% we have increased the accuracy. Okay. And here you can see the clear difference between the result before hyperparameter tuning and results after the hyperparameter tuning. So this side, this left side has results before hyperparameter tuning, and in this side you can clearly see the results after the hyperparameter tuning, which is giving the best detection accuracy. Okay. So later we selected that model, and we used this model for the deployment, and we deployed model using the Streamlit framework, because it is easy and fast UI development on the Streamlit side, and which is user friendly interface. Okay. The Streamlit has the user friendly interface. So this is how our Streamlit UI looks like. So here we can browse or we can drag and drop our images, palette images, and then it will give you the detection count. You see here, it is accurately detecting the number of palettes. Okay, and the conclusion is the YOLO V8 large best palette counting system has successfully automated a manual and error-prone process. It delivers a real-time high accuracy result with the minimal delay. The solution has improved inventory tracking, reduced cost, and boosted overall warehouse efficiency. It demonstrates how AI can solve the real business problem and deliver the measurable values. Basically, our solution is helping the company to count the stacked pallets in the real time using the YOLO V8 large model. Okay. It works with the warehouse cameras to automatically detect and count pallets quickly. So taking less than 1 second per frame. Okay. So this has reduced the need of manual counting, improved the inventory accuracy, and made the delay operational faster and smoother. As a result, the company has saved 25% of warehouse cost and reduced inventory losses by 30%. Okay, it's making the entire process more efficient and cost effective. Okay, so this solution we have provided, and this is all about today's project. Yeah, thank you. Thank you. That's it for today.